Okay, so let's talk a little more about the 3D infinite swept wing. In this 3D infinite swept wing, it's a very special case because if you look at the pressure distribution, right? So if you look at the pressure distribution, so let's actually define the surface coordinates first. So let's define this coordinate to be x and this coordinate to be the z. So this is a case where you can have a global coordinate system that is not only orthogonal but also has unit normal. Right? You can define a perfectly regular grid on this airfoil. And every grid is going to be square and of the same size. Right? Okay. If you do that, first question is, how does the pressure vary in the z direction? Zero, right? That's the same argument we have. If you go from here to here, there shouldn't be any pressure variation. Okay, so partial P partial Z is going to be 0. Now combine that with the momentum equation outside the boundary layer. So if you think of the momentum equation outside the boundary layer, the dpdz is equal to what? Dpdz is equal to, we just looked at over here, dpdz is rho ue times dw dx plus rho we times dw dz. Okay, so dw dz is always 0, right? We said everything has a 0 derivative in the z direction because of the infinite nature of the swept wing. So this is this component is 0, so that means 0 is equal to rho ue times dw dx. Now what does that mean for dw dx? We know ue is not 0, right? Ue is the component downstream, not downstream, but like pointing towards the trailing edge in a direction normal to the leading edge. That's x. So ue is not 0. The only consequence is what? dwe dx is equal to 0. So that means dwe dx. Okay? So we has 0 derivative in x direction, and of course it has 0 derivative in z direction. So what does that mean? We is the same everywhere, right? And that happens for, so this equation is true for anywhere outside the boundary layer. As long as we don't have viscous effects to change the governing equation, this is the same, not only for we, but for any w anywhere. The x derivative is 0, z derivative is 0. Okay? So w is uniform. Everywhere, not just outside the boundary, not just immediately outside the boundary layer, but everywhere outside the BL.
WE.
No, W is uniform, right? So we analyze. So this is true for the equation that doesn't have viscosity. Right, so it is true for the velocity just outside the boundary layer. It's also true for velocity far outside the boundary layer. Right, so this is true for anywhere other than in a thin layer near the wall. So that is the basis of this special case. Now with that, the thin layer equations can be significantly simplified. So first of all, the mass conservation equation, partial u partial x plus partial v partial y plus nothing equal to 0, right? Partial w partial z is equal to 0. So the mass conservation equation is the same as in 2D.
But this is for outside the boundary layer.
Oh, this is for out, right. So okay, so this is for outside the boundary layer. So this is for outside. Okay, so this is for outside the boundary layer, which means that we can, the mass conservation equation is the same as 2D for the outside the boundary layer. The momentum equation is also the same for 2D outside the boundary layer, right? So this is the mass momentum equation. So every equation outside the boundary layer is the same as the 2D case. That means the pressure distribution or the UE distribution outside the boundary layer is also exactly equivalent to the 2D case. So for outside, so let's just say that UE distribution is same for 3D versus 2D. Okay, so for inside the boundary layer, so we still need the full mass conservation equation. But still dWdz is 0, not because W is 0, but because any ddz is equal to 0, right? So this is because of ddz is equal to 0 for the infiniteness of the swept wing. As you move towards the z direction, anything doesn't change. So that's momentum equation. Oh, that's mass conservation equation. Also, we have the momentum equation. So let's get rid of the rho, divide rho on both cases. U times du dx plus v times du dy plus nothing times du dz, because dz, any ddz is equal to 0, right? That is equal to ue times due dx. And also the due dz is gone because ddz is equal to 0. So this plus partial tau xy partial y. So this is the x momentum equation. So looking at the whole x momentum equation and mass conservation equation, we find that it doesn't involve any w at all. What does that mean? That means the solution for the thin layer equation is the same for 2D versus 3D if you ignore the w component. Or in other words, the w component of the velocity is decoupled from the uv component for an infinite swept wing. You can solve the uv component exactly following the same equation as the 2D case, and then as a second step, solve for w. So this is the first step. You get the same as a 2D solution, and the w component can be solved once you have these equations. And the w component is simply u times dw dx plus v times dw dy, and because you solve the second step only after you have u and v, so this is like a linear equation. This is equal to ue times partial we partial x, which is 0, right? Because we is constant. It's constant. So this is in other places we eliminate the w's because the z derivative. In here we eliminate even the x derivative because our previous analysis over here that shows you the w velocity outside is always constant. Okay, and also plus the other one is a z direction derivative, which is going to be 0 anyway. And what you left is d tau zy dy. So this is also 0. So basically, you solve for the uv velocity from the 2D analysis and then get the w velocity. So that is true for any geometry that is infinitely long in the third dimension, or doesn't vary for infinite length in the third dimension. Okay.
So in this case, then, like the U and V would not change compared to the 2D case, right?
Would not change.
And
That's
it
right.
only has an extra W component constant
Exactly.
that's superimposed on it.
So outside the boundary layer, it has a constant W imposed on it. But inside the boundary layer, that W is no longer constant. That's right.
It's just a function of X and Y, though.
It's just a function of X and Y. Nothing is a function of Z in this case. Yeah. Okay, so you can do that, not just for an airfoil, but for any flow that is homogeneous in the third dimension. For example, you can solve this for Faulkner scan flows, right? For Faulkner scan flows, you have a change of UE that is of polynomial form in the X direction. And then if you impose a uniform Z flow on the Z direction, you can go through the same procedure to solve for what is the corresponding boundary layer, what is the corresponding cross-flow profile for the Faulkner scan solution. So if you do this for Faulkner scan solution, you get the so-called Faulkner scan Cook profiles that are 3D. So if you have a IBL solver for laminar flows in 3D, instead of using the Faulkner scan solutions to obtain your closure, you use the Faulkner scan Cook profiles to obtain your closure. And solving this is a pretty small step on top of the regular two-dimensional Faulkner scan flows, just because the third equation is decoupled. All right. Oh yeah, one last thing I want to discuss. This is these two equations are mathematically decoupled only in the laminar case. So if you have turbulence, these two steps can actually couple in both ways through this tau xy, right? Because the existence of a W velocity is going to change the intensity of turbulence, and the intensity of turbulence is going to change your tau xz, your tau xy, right? So the coupling is actually formally two-way in turbulent flows. But empirically, we find the coupling to be very, very weak, because essentially what this W velocity do to the flow is adding a little bit more turbulence, right? And turbulence is actually remarkably insensitive to Reynolds number. I mean, it is sensitive, but you have to usually change the Reynolds number by a large factor, like a factor of 5 or something, to see a significant difference in the turbulent statistics. So changing the velocity by a factor of 20% doesn't really change the turbulence that much. So you can pretty much use the same turbulent viscosity, which then it's still going to be the same. So even in turbulent cases, we can comfortably make the approximation that we can solve for 1 first and solve for 2.